Before is titled Angles and Sides of a Triangle of Triangles. It covers pages 25 to 27. And we are going to answer the question, what other relationships can I find? So for question 104, it says, Marcos decided to change his tiling pattern by drawing diagonals in each of the parallelograms. So the other day, we had this similar pattern, but it was just the parallelogram. Now he's drawing in diagonals. The diagonals cut that parallelogram and makes it, each of them create two triangles. Okay? So for part A, they want you to use a colored pen or pencils or highlighters, whatever you've got, to shade one of the triangle's angles. It says to use tracing paper. Well, we're just going to do it right on here. But if you need to use the tracing paper, you can. You're going to use the same color to go through all of the triangles and highlight the same color to shade every angle the same, that is congruent to it, to the same shaded angle. You're going to repeat this process for the other two angles of the triangle using a different color. So you'll end up needing 3 different colors because triangles have 3 angles, right? Okay. When you are finished, every single angle in your tiling should be shaded with one of the 3 colors. So I used pink, blue, and yellow. So I made the small one yellow, then I made this one blue, and this one pink. Whatever different colors you have, just make sure that when you go through, they're all the same. So all of the triangles facing this way, the top angle is going to be pink, but the 2 facing the other direction, the bottom angle is going to be pink. Does that make sense? Because they're rotated. They're turned. Okay? All right. Now, once you are done, you're going to come back. You're going to examine your colored tilings, and you're going to see if you can figure out a relationship. So what relationship can you find among the 3 different colored angles? What does this tell you about the angles in a triangle? Write a conjecture, and it starts the conjecture for you right here. It starts with if a polygon is a triangle, then the measures of its angles, and if you can figure something out, you're going to write it right here. Okay? That leads us to part D, which is the first E tool that I showed you. It says, how can you convince yourself that your conjecture is true for all triangles? Use the diagram below, and your knowledge of angle relationships, if the technology is available, which it should be, you should be able to get into the ebook. You're going to go to question 104. You're going to click on the blue hyperlink for the E tool, and you can move those vertices just like I did, and you're going to see what happens with the sum. I showed you a couple, but if you need to go back in there and convince yourself, you can do a couple more. But you should end up with part E, which says, use what you know about angle relationships and parallel lines to prove your conjecture. This will be referred to as the Triangle Sum Theorem. You should be able to take all 3 angles. We'll call them angle A, angle B, and angle C, and you should get the same measure every time. So where I have my question mark, you're going to write the angle measure that you get every single time, whether you change those angles on the triangle, right? Anybody think they know what it is? All hands shoot up because it's kind of obvious. Yes. 180 degrees. Good. Okay? So it should be 180 degrees. If you need more convincing, go to the E tool. Try a bunch of different ones. It'll always be 180. Okay. Flip over to the top of page 26. Question 105 says the triangle inequality conjecture. Okay. This one is a little more complicated, but it's not horrible compared to always equaling 180. It says, now that you have proven the triangle sum theorem, you can always determine the third angle measure of a triangle if you know the measures of the other two angles. Should say side. Is there a similar relationship among the side lengths of a triangle? That is, if you know two side lengths of a triangle, can you determine the two sides? So for part A, it says, first discuss this question with your team. Consider a specific case. If a triangle has side lengths of 6 centimeters and 8 centimeters, what do you know about the length of its third side? Okay, so this particular triangle, on the right, you have a side with 6 centimeters, and you have a side of 8 centimeters. How can you get the measure of that third side? There's one specific way you could get it. It's a very specific case. Yes? If it's a right triangle, you can use a theorem. Does anybody know the name of the theorem? The Pythagorean Theorem. You could use the Pythagorean Theorem to get that third side, and you would get the exact measure. But it doesn't have that little box. You know, you should see that little box right there, and it's just not there. So that would be the only way we could for sure determine it, but we don't have that. So if you don't have that, how can you get the third side? Well, Jeannie says that the third side could be any length. And Mary says that is not true. For example, the third side could not be 100 centimeters long. Who is correct? Jeannie or Mary? Okay, think about it for a second. If we come over here and I draw on the board a side that's 6 centimeters and a side that's 8 centimeters, could you have a third side that is 100 centimeters long? No, it's way too big or way too long, right? How about, could I have a 1 centimeter? This was only 1 centimeter, and we brought this 8 over here. What's going to happen with the side that's 8 centimeters? That would be too long. So that means that 1 centimeter is too small, right? 100 is way too big. 1 is way too small. So how do we get that third side? Okay. Part C. If a triangle has side lengths of 6 centimeters and 8 centimeters, what are the largest and the smallest possible lengths for the third side? You can go to that second tool that I showed you, which is the Triangle Inequality tool, and you can figure it out. So I drew on the sideboard of the 100 and the 1. Basically what you're going to do is you're going to take the two side lengths that you know, you're going to add them together. So you're going to take the 6 plus the 8, you get 14. Then you're going to subtract them. You're going to take the 8 minus the 6, you're going to get 2. Then you're going to write it as an inequality. That third side needs to be less than 14, but not equal to 14. It can't be exactly equal to 14. It has to be a fraction or a decimal less. Like you could have 13.999, but you can't have 14. 14's too long, okay? Same thing with the 2. X has to be greater than 2, but notice we don't have the equal part, okay? Don't draw the equal part because it can't be exactly equal to 2. It'd have to be 2.1 or 2 1/3. So it'd have to be some decimal or fraction larger than 2, okay? So with your team, you're going to come back and answer part D, which says, which of the sets of side lengths below can be used to build a triangle? How can you determine this without using a tool? So you can either use the E tool that I showed you, where you drag the little slider, see if 5, 3, and 10 will make a triangle. So you're going to say yes or no for numbers 1, 2, 3, and 4. You need to go in and use the E tool, go in and use the E tool. Then when you're done, you're going to do part E, which says generalize your findings for a triangle that has any side lengths A and B. If a triangle has side lengths A and B, what are the possible side lengths for side C? Hint, look at part C, okay, where I did it with 6 and 8. Okay, I took 6 and 8, I added 6 and 8, and then I subtracted 6 from 8, okay? That's what you're going to do with A and B. All right, flip over to the top of page 106, page 27, where it talks about the longest side and the largest angle. While Maria was building triangles, she noticed another relationship. To make a triangle with one side much longer than the other two, she had to make one of the angles much larger than the other two angles. She measured the angles and sides of one of her triangles and drew the figure at right. In Maria's figure, side AC is opposite angle AB. What do you notice about the length of AC compared to the other sides of triangle ABC? What is the relationship of angle B with the other angle measures in triangle ABC? Okay? So if you put your finger over here on angle B, there's a 127, right? It's the largest of the three angles. So you have a 21, a 32, 127 is definitely the largest angle, right? Go to the opposite side and you have a 9 centimeters there. And then compare it to the other two sides, the 4 and the 6. It's definitely the longest side is going to be opposite across from, so you can go like this, go across from each other. The longest side is going to be opposite the largest angle. It's going to be true for the part B. The shortest side, so 4 centimeters over here is the shortest side, is going to be opposite the smallest angle. So you go to the opposite over here, and there's the 21, which is definitely the smallest of 32 and 127, right? And there's no such word but as middleist, but if you go to the middleist side and go to the opposite angle, it's the middleist and middleist, but we generally just look at the longest and the shortest, okay? Part C says, if triangle ABC has side lengths of AB, which is 4 centimeters, BC, which is 9 centimeters, and AC, which is 12 centimeters, then which angle has the largest? So you look for the longest side. Is the longest side 4, 9, or 12? 12, right? So if 12 is side AC, the angle that's opposite that is going to be angle B. Angle B will be the largest angle, okay? Which one will be the smallest? Well, you find the smallest number, which is 4. That's side AB. That means that the angle opposite would be angle C, is going to be your smallest, okay? And the last question is the same, except for we have a tie. Watch what happens. If you have a different triangle ABC and you have one side that's 10 centimeters, another side that's also 10 centimeters, and a third side that's 12 centimeters, then which angle has the largest measure? So that's clearly the longest side, right? So the opposite angle would be B. That's going to be your largest. But then we have a tie for the shortest. This is 10 and this is 10, right? So we have a tie for the smallest. So opposite this one would be angle C, and opposite this one would be A. So we have a tie between angle A and angle C. That means it's what kind of triangle? If it has two sides that are the same measure. Isosceles. What if we had a three-way tie? Could